here we are, 5-6, day 2. We're going to do a little recap of the mean value theorem and Rolle's theorem. We're going to start this first one with a story problem involving the mean value theorem. And what it is compound interest. It says, this is actually your number 11 in your book, but you don't need your book. You are going to invest $1,000 in a retirement account. And this retirement account has an annual percentage rate of 9%. And the equation that gives you the amount of dollars after T years is 1,000 for your original investment and the 1.09% interest raised to the T years. So DT is dollars in the account, T is years. And let's take a look at, well, let's just see. It says when you retire 50 years from now, how much money will be in the account? So how much money after 50 years? So we're just looking for the number of dollars we'll have after 50 years. So I don't have to do any calculus. This is simple algebra. Plug in the 50 for the time. So the dollars at 50 years is whatever 1,000 times 1.09 raised to the 50th power is. And I'm assuming you can do that on your calculator. And it is somewhere that I have hidden. Oh, quite a bit. $74,000. $74,357.52. That's quite a bit of money. Okay, part B says, at what average rate does your money increase? So the average rate is, well, let's look at the graph before I jump right into it, assuming you know what to do. Let's take a look. 1,000 times 1.09 raised to the x, and I'm starting with $1,000 at time 0, and I'm ending there, so my window's going to have to be, for x values, for the y values, quite big. So if I started the y's at 0, and I know I've got to get up to like 75,000 to see the 50 years. So I'll go 75, 1, 2, 3. Okay, and the time went from 0 to 50. All right, let's see what we get there. So there's my money. Starts growing rather quickly as it goes out. Okay. So it does this. Okay, it's asking me for the average growth rate. Remember, the average is if it was continuous, if it was linear and grew the same amount each year, which it does not do, but it would be the slope of this secant line if that was 50. So I'm looking for that slope. So I need the x and y values at each spot so I can do rise over run, change in y over change in x. So this was time 0, and I know I started with $1,000. So that's 0, 1,000. Then at 50, we calculated that $74,357.52. So to turn that into a rate, the slope, change in y, 74,357.52 minus the 1,000, divide by 50, and you get $1,467.15 per year. That's if it grew the same amount each year, but it does not. It grows a little here, then it starts at the end climbing exponentially. Okay, now it says differentiate numerically to calculate the instantaneous rate at which your money is increasing now and when you retire at 50. So we want the instantaneous rate. So we want the slopes at these 2 points. So we want the slope here. I mean, I know it looks a little linear, but it's not going to be. And then we want the slope here. That will give us our instantaneous rates at those 2 spots. So for part C, we want the instantaneous rates at time 0 and time 50. So we want the derivative values at 0 and 50. Okay, we can't do this algebraically because we have yet to learn how to do the derivative with the x up in the exponent. So we have no choice but to use the end deriv on this one. So for x equals 0, you're going to go to your end deriv. You type in the function 1,000 times 1.09 raised to the x, comma, x, comma, and I want this done at 0. And then I want to do it again. 1,000 times 1.09 to the x, comma, x, comma, 50. I got too many parentheses going on in here. Get rid of that one. Okay, and I'll let you take the time. Well, I'll do one and you're going to do the other one. So, math. And deriv. The equation is 1,000 times 1.09 raised to the x, comma, x, comma, 0. So it was going up at $86.17 per year when I first put it in. Oops, I was at the wrong line. And I want you to repeat it with a 50 and fill that value in. And you see it should be quite a bit more. Look how vertical it is. And then our last question is to find the time in here. Find the time when the instantaneous rate equals that average rate. So remember, we're looking for, there's our average rate, this linear function here, that slope. The instantaneous is the tangent line that has that same slope, so about there. We want to know that year. So again, we would, if we were able to do it algebraically, we would do the derivative of this and set it equal to that average rate that we found. But we can't do this algebraically, so we have to use the calculator. And what we're going to do is graph the derivative function and trace. So we're going to graph and trace. So I'm going to go to y equals. Get rid of that function. I want it to graph the derivative function. 1,000 times 1.09 raised to the x, comma, x, comma, x. It'll do all of the x values then when it makes the graph. And I only need it to go up to, because I know my derivatives are, I'm going to max, well, I want it to be this, so maybe I'll go to like 5,000. So window, I'll have it go to, see if 5,000 is enough. Oops, 50,000. And remember, it's got to do each calculation. Okay, so I had this go up to 5,000. I want 1,467. So I want it's right about in here. So I'm just going to trace until I get this y value to be close to my 1,467. Okay, and that's the best we can do. We cannot do this algebraically. Yeah, so it's somewhere between 32.4 and 32.9 years. I mean, if I want to zoom in, but that's close enough. So about 32 and a half years. That's in the ballpark enough. Okay, our last example is going to go back to Rolle's theorem from yesterday. And I want to do a quick review of Rolle's theorem, the three sufficient conditions for Rolle's theorem. Remember, between two zeros, there should be a derivative of 0. And the three conditions were the function was differentiable, f differentiable on the open interval from a to b. So it didn't have to be differentiable at a and b, just in between them. The second one, it had to be continuous at a and b, f continuous at a and b. And the third condition was that f of a had to equal 0 and f of b had to equal 0. If those three conditions were met, then there was a c value in between here where f prime of c equaled 0 and c was in the interval from a to b. That was our conclusion. All right, the chunk of problems in the book, I'm going to do number 19. Asks you to do several things, 3 things for each problem. Sketch the graph. State which of the 3 hypotheses are not met, if any. So, which hypotheses are not met? And then also, even if they're not met, Rolle's theorem can still have this derivative equal to 0 in that interval. You have to say whether the conclusion is still true. Is Rolle's conclusion true? Okay, so those 3 things. In number 19, the equation is f of x equals x squared minus 4x. And the interval that's given is from 0 to 1. So if we take a look at the graph, okay, you'll have good practice with windows on this assignment. X squared minus 4x. Okay, I'm going to go back to a zoom 6. And I am only looking at the graph from 0 to 1. So if I wanted to change my window so that I only see x from 0 to 1, it was just that part of the graph going down. If I go back to a zoom 6, you can see all it graphed was this little decrease here, but because I stretched it way out, that's why it looked a little different. So